for the second talk. And I will start by recalling the main points of our discussion yesterday, because it's never bad to recall what we have done. So the first point we discussed yesterday was a theorem by Griffiths, saying that if V, let's say in Pn is smooth, if D is a degree, then there is an interesting identification between some homogeneous components of the corresponding Milnor algebra and some spaces coming from the Hodge decomposition of the middle cohomology. And this zero just meant we look at primitive cohomology. Second point was that if I consider now V with isolated singularities, essentially there are only two interesting cohomology groups: the middle cohomology group and the middle plus one. And moreover, the difference of dimension is known, because this is just Euler characteristic, modulo something perfectly understood. And so it is enough to compute, if you are interested only in Betti numbers, if it is enough to compute only one of these two dimensions, right? The dimension of these two vector spaces. And as a general rule, this space here has a tendency to be large, and this space here has a tendency to be small. And so I will explain at some point how can we handle the computation of this space. For instance, for nodal hypersurfaces. Okay. And then it was a very rapid recall on mixed host structure. And I will continue a little bit this recall, because we stopped in an abrupt way because it was a time to stop. So now I will continue a little bit on this abstract stuff, and then I will go back to these points and discuss a lot of concrete things today. So it will be an easy lesson. So we have defined essentially what is a mixed host structure. So it's a triple H, which is a Q vector space, some wave filtration, and some Hodge filtration. And of course, the main theorem is a theorem by Deligne, saying the fact that for any algebraic variety X over C admits natural mixed host structure on its cohomology, and now I will just explain a little bit why this is so important. Because natural means that if we have if we have two algebraic varieties and a regular mapping, which is a usual morphism considered in algebraic geometry, then this induces, as you know very well, morphism at cohomology level. And these morphisms are compatible with this, all this filtration in the sense that if I take the image of some step of the filtration, WK here, I get something inside WK here. And if I take the image of FP filtration, I am inside the FP filtration. And moreover, this morphism is strictly compatible with this filtration. And what does it mean? Strictly compatible means that if I have, let's say, an exact sequence of mixed host structures, something like that, then I can take, for instance, the host filtration and the sequence remains exact. So this is for any p, and here is for any k and any p. And the same for the wave filtration. And so the advantage of having such a structure is that as soon as we have some exact sequence, we get a lot more exact sequences by putting the filtrations to play a role. So this is why, in my opinion, these objects are quite important. Okay, any questions still here? Yeah?
How far does this extend? Is for Keller space?
For Keller spaces, of course, if you have a compact Keller manifold, you have the usual Hodge decomposition, right? Now, if you have something which is called a quasi-Keller manifold, which is a complement of a normal crossing divisor in a compact Keller manifold, then you can construct a mixed host structure on the complement, but it's no longer functorial. So there are some problems with functoriality. This is what I know.
The homology is just the ordinary Betti singular homology.
Yes, yes. Here is a singular homology. Yes.
Sorry, there's nothing analogous for non-reduced schemes, projective schemes.
For non-reduced projective schemes, I don't think there is a theory over complex numbers. Maybe there is a theory related with L-adic cohomology and filtration by weights. Maybe. Yes. I am not a specialist in that area, but here I am pretty sure you cannot do it. At least it was not done until now, sorry. Yes. It was not done until now. Maybe some of you, strong young people, you will extend this to non-reduced schemes. But I have not seen until now such an extension. Okay, other questions? Good. Then we can continue. You see, if I go back to the first point here, I see that only some of the homogeneous components of the Milnor algebra have a geometric interpretation. And I can ask myself, what about the others? And the answer is very simple. So now I will discuss something relating to the first point, which can be called Milnor algebra. And Milnor fiber. And so I will discuss this for homogeneous polynomials, but the theory goes very well for weighted homogeneous polynomials, and I will give an example at some point of a weighted homogeneous situation. So let's say we have a G homogeneous polynomials in Y1. Here is very difficult to decide which notations to use. Anyway, suppose G is a homogeneous polynomial of degree D, and I consider the Milnor algebra. You know what it is, so it's a polynomial ring divided by the Jacobian idea of G. And I consider the Milnor fiber of G, which is the set of points Y in Cn such that G of Y equal to 1. And I will assume that this is finite dimensional, which is equivalent, as you have seen, to the fact that G equals 0 is an isolated singularity. Right? And then it was known by the work of John Milnor, the following fact. So theorem, essentially John Milnor, and some point maybe Peter Orlik. First of all, the topology of the Milnor fiber. The topology of the Milnor fiber is very simple. Fg is homotopy equivalent to a bouquet of sphere of dimension n minus 1. And the number of spheres, so the n minus first Betti number, is exactly the dimension of this space, which is called the Milnor number of G. So this is a relation between Milnor algebra, Milnor numbers, Milnor fibers for homogeneous polynomial and for weighted homogeneous as well. And the second point is that we can actually do something similar as in Griffiths' theorem. We can identify a basis here with the basis in the cohomology using differential forms. And I will explain this. So I take here a monomial, so always one can choose monomial basis, and to such a monomial basis we associate the cohomology class of this, which is an element in Hn minus 1 of f, with coefficients. And omega is the form which I defined yesterday. Yesterday there was variable x, now variable y, but it's the same definition. And omega is the differential form of degree n minus 1. And so this defines a cohomology class here. And the theorem says that this is actually a bijection. Sending a basis here is sent to a basis there. And moreover, there are some relation exactly as in Griffiths' theorem with the mixed Hodge structure here. So here we have a mixed Hodge structure because we have a smooth, non-compact algebraic variety. And I will not go into detail because this is not very important. What is more interesting for us is that the Milnor fiber has a monodromy operator, right? So it has a monodromy operator, which is just multiplication by this root of unity. And because of this description, we can describe in a very precise way the eigenvalues of the corresponding monodromy operator. So this operator is semi-simple. Since HD is the identity. And so to determine it, it's enough to determine the eigenvalues. And the eigenvalues are easily determined because we have this very precise description of a basis. And that's it for the moment. Maybe we can make an example here. I will give an example which is weighted homogeneous, but the same result applies. So assume that G has this form. For some integers which are at least 2. So these polynomials are called Briscoe from polynomials. And in this case, one can describe the eigenvalues of the monodromy in the following way. I will write and then I will explain what I mean by this notation. So the eigenvalues of lambda is a set. And this set is obtained as follows. I take the roots of unity of order A1. This is a multiplicative group, right? And I throw away 1. So this star means I throw away 1. I keep just the roots of unity different from 1. And I do the same for all the others, A2, AN. And then I consider all the possible products. All the possible products. And in this way, I get exactly the set of eigenvalues of this with multiplicities, because maybe some number will appear several times as such products. And so this is a description.
So when you're writing the above line, you're writing
Yeah.
h of y equals lambda times y.
Yes?
You don't intend that every eigenvalue is multiplied by the same.
No, no. This is the definition of the monodromy operator.
From the back.
But you don't mean that every lambda, that every y is multiplied by the same lambda.
Yes, I mean it's the same lambda for every y, and this is the definition of the monodromy operator. But eigenvalues are something different. They are roots of unity of order d, but all the roots of unity.
The monodromy acts on the fiber and H star is in cohomology.
The y you're writing down there are monomials, or they're the basis, they're yi.
Y is just an element here. So the monomials occur only here, and for the rest, y is just a point. And this definition of monodromy comes from the fact that the polynomial is homogeneous.
So in the line that you're saying now is the definition of monodromy.
Yes, this is
Y
the...
is no longer a monomial.
No, here y for any y in Fg.
Yeah, for weighted homogeneous polynomial, the operator H is not the
Yeah, of course.
for lambda.
Of course,
Lambda
of course.
to the power.
Of course, of course, of course. So I will do some explanation. Suppose that G is weighted homogeneous of type W1, W2, Wn, and the degree is n. Then the definition of the monodromy is something like that. And all these are supposed to be integers, strictly positive integers. And the usual homogeneous polynomials are homogeneous of type 1, 1, 1, and D. This definition generalizes this definition of the monogram. Yes, please?
So it seems really surprising that the monodromy acts on space and not just on cohomology.
Yes. So in a more complicated situation, the monodromy is a lift of something in the base of the vibration, and there are several choices, all of them homotopy equivalent. But here, because the polynomial is weighted homogeneous, we have this canonical choice. And moreover, this canonical choice is an algebraic mapping. And that's why the monodromy operator is compatible with Minkowski structures. So there are a lot of advantages.
The H is a diffeomorphism.
Yes.
Just by
Exactly. So is the monodromy of the vibration? Yeah.
over the unit circle.
Yeah, exactly.
It's a C infinity pattern.
Exactly.
And you're trivializing.
Exactly. Exactly.
Yeah, but the fact that you can identify the Milnor fiber with this affine polynomial that comes from the fact that you have a weighted homogeneous polynomial.
Exactly. Yeah.
Otherwise, it's not.
Otherwise, we have to work locally. I am very glad you have questions.
In any case, you just get down to some kind of monomial game.
In-
Monomials and weightings.
Yes. But some weighted homogeneous polynomial are not sum of monomials, so you have to be more careful. But it's a class that we can handle well. That's why I discuss this class in detail. Yeah. Okay. Other questions?
Did you tell us where the grading appears in the cohomology of FG, or are you still coming to that?
You mean the weight and the Hodge filtration?
So the Milnor grading.
Yes. Yes.
That cohomology of FG.
Yeah. So I do not insist on that. So here the grading is related with eigenvalues of the monodromy. But for one eigenvalue, I get several components. And if I want to localize the one component corresponds to some eigenvalue plus some stage of the Hodge filtration. So if I want to fix one component, then this means I fix an eigenvalue and I fix a stage of the Hodge filtration. Okay, good. So I explain you what we can do with the other homogeneous components, and this was my upgrading of the first point. Now we go to the second point and we do an upgrading of the second point. So, the upgrading of the second point there has a title, if you like. When do we have in some cases, we can say that one of the unknown primitive cohomology groups are 0 for trivial reasons. And I will explain you what does it mean. And to do this, suppose A is a singular point, and we consider this germ. And this germ, of course, I can represent it in a ball, and I can take the intersection with a small sphere, and I can get the link of the singularity. So this is a sphere in the n-dimensional space. So is a sphere of dimension 2n minus 1, center at A, and with a very small radius. And this is called the link of the singularity. And in Milnor's book, you have a proof that the topology of this is a real manifold, real 2n minus 3 compact oriented manifold. And the topology does not depend on the choice of epsilon. This is shown in the book by Milnor. And moreover, if I look at the Betti numbers of this of such a link, I get the following sequence. I get 1 because something is non-empty and connected. So I forget to say I will consider in all my talks n strictly bigger than 1 to avoid some special cases. For instance, here if n is equal to 1, I have to take reduced homology or cohomology, and so I will consider n strictly bigger than 1. Anyway, for you, the most interesting case is n equal 4, so it doesn't matter if we take n bigger than 1. And so then we get some a sequence of zeros, and then we get the middle Betti numbers, which are 2 in this case. So they are n minus 2, n minus 1, and then again 0 and 1. And moreover, these two Betti numbers are equal because we have Poincare duality. And now a definition. We say that LA is a Q-homology sphere if these Betti numbers vanish. And so with this definition, we have a fact that if all the links LA or A in the set of singularities of E are cohomology spheres, then the corresponding primitive group is equal to 0. And the proof is very simple if you are an expert in algebraic topology, because in algebraic topology there is a notion of not only of a smooth manifold, as everybody knows, but there is a notion of a Q manifold. A Q manifold means exactly that each point has a link which is a Q homology sphere, which is the case for an usual manifold. You agree with me? And in algebraic topology, they show that as soon as you have a Q manifold which is oriented, this is our case, then you can apply Poincare duality over Q. And in our case, Poincare duality over Q will relate this group to Hn minus 2, maybe dual, and this is 0 because in n minus 2 we have no problems. And just to give you the answer from the very beginning, now we are interested in computing when to decide if this is 0 or not. We like to be able to compute it, and there is another simple fact that this interesting Betti number is just a multiplicity of 1 as an eigenvalue of the corresponding monodromy, so I will denote it by HA. So the singularity at A maybe is not weighted homogeneous, but in any case, it has a local Milnor fiber, as defined in Milnor's book, and it has a local monodromy, and eigenvalue 1 can appear, and the multiplicity of 1 as an eigenvalue is exactly this useful Milnor number. And so now let's give an example. So what happens for nodal hypersurfaces? So assume we have a nodal hypersurface in Pn. This means that the local equations for any singular point is just the sum of squares. And this is exactly something of brisk confound type. What are the eigenvalues? If I do this, I see that the only possibility is minus 1 power n. So there is just one eigenvalue. And this is obtained by taking minus 1, minus 1, minus 1, making the product. And this is, and now you see that this implies that the corresponding Betti number for a node is 0 when n is odd, and is 1 if n is even. And what is the conclusion now? If I combine this example with this proposition, you see that if the ambient dimension is odd, then nodal hypersurfaces cause no problem for the computation of the Betti numbers, because one of the two mysterious numbers is 0, and I know the other because I know the difference. Okay. Very good. And so now we see that essentially the difficulty, if we look at from the local point of view, and the difficulty of computing this number is related to the size of this Betti number. If this Betti number is 0, no problem. If it's small, like for nodes, maybe we have some chances. If it's big, and this can be very big, then the chances decreases to be able to make such computation. All right? Very good. And so we have seen that for the Milnor fiber, we have a nice description. For the Milnor fiber cohomology, we have nice description in terms of differential forms. We can ask, can we do something similar for this, for the cohomology group of the link? Because if we can do this, maybe these local differential forms will come into play. Yes, please.
N should, in your color, N should be 1 plus 1, or not?
Sorry. This is in this case.
No. The same.
Yeah. Other questions?
Yes, in general, this
Yes.
A,
Yes.
the real
Link.
manifold, what does it look like? Isn't this like, I mean, as a real manifold,
Yes.
is this like one of these called some handle?
There is a, I think this is a 2n minus 3 manifold, which is n minus 2 connected. This means that n minus 3 connected. It has a lot of 0 here. And so there are good understanding of such manifolds. But I am not able to tell you. In case of surfaces, for instance, these are related to length spaces. If you have surface singularities, these are length spaces and plumbing manifolds and things like that.
Okay, and in general, why, I mean, is it obvious that there are all these zeros between?
Yes, this is a Milnor theorem.
Okay.
It's a theorem. Yeah.
But they're not just manifolds, they're knots inside.
Exactly, I agree with you. I agree.
That's the more subtle point.
I agree with you. Yeah, and we will come to this point. And the fact that they are knots are reflected, for instance, in this proposition.
Yeah.
this proposition comes from that. Fact.
Yeah, a link is unknown if the point is move point. Yeah.
Yes, yes, yes.
You know, topologically smooth and differentially smooth are not the same.
Yeah, but
Look, it's complicated.
yeah, but for complex hypersurface, if you have, I mean, you cannot never have a smooth manifold around a complex hypersurface. I think it's in a Milnor book.
Milnor has these exotic spheres that are homeomorphic spheres, but not different spheres.
Yeah, we can discuss later. This becomes too technical. Other questions?
Yeah. Is there an easy, understandable idea behind the second proposition?
This?
Yes.
This is exactly what Professor Miles Reed has said. It comes from the fact that we have the sphere and the complement of the link, these fibers over the circle with the fiber, the local Milnor fiber. And if you write the one exact sequence of such a vibration, then you get the result using some duality. Because the Betti number of this is the same as the Betti numbers of this using some Alexander dualities. Okay, very good. And so now our aim is to try to understand the description of this middle cohomology of the link using differential forms. And so our aim now describe and this, I will describe this, how to attain this aim only in the weighted homogeneous case. And so to do this, we use again using sequence. Associated to a smooth divisor in a complex manifold. And the complex manifold is just a disk of radius epsilon, center at A, let's say, with the origin deleted. So I'll put it's not a disk, it's a ball. It's a epsilon. The ball center at A of radius epsilon and with the center deleted. And here is V epsilon, which is the trace. So V epsilon is D epsilon intersection V. And V epsilon star is V epsilon minus. And so now, because I have an isolated singularity, this means that I have a smooth surface in a complex manifold, and I can write the Gisin sequence. And the Gisin sequence in the middle has this form. Okay, so I have these two zeros at the end because the puncture ball has a homotopy type of a sphere of dimension 2n minus 1. And so with my assumption on n, that is n strictly bigger than 1, you can check that these two spaces, this cohomology group, are 0. And this means that the residue, the Poincare array residue is an isomorphism. And moreover, this group here, again by Milnor, this is just h n minus 1 of the corresponding link. And so in order to compute the cohomology of the link, I can work on the complement of the hypersurface germ. And I can do some tricks here using differential forms. Okay, so now I will give you the description of Hn d epsilon minus the epsilon for VA weighted homogeneous isolated singularity. And so I will suppose that this germ is defined by a polynomial as before, and I assume that G is weighted homogeneous of type W1, Wn, and capital N. And all of these are integers. And then the corresponding Milnor algebra is again a graded algebra. using the grades as the degree of xj is equal to wj. And I consider a differential form omega n, which is a top differential form. And the weight of this is just the sum of the weights of the differential. Like that. And now I can describe you by saying that the basis for this space has a form y alpha, so here is a monomial, omega n divided by g power k, where y alpha is a monomial basis of some homogeneous components of the Milnor algebra, so mu g s with s plus weight of omega n equal kn. So the idea is that because we work, it's a little bit like working on a projective space. We want that the denominator and the numerator have the same degree with respect to the corresponding weights. And why this is so? This is so because the monodromy operator, which I introduced short time ago, acts on such differential forms. And such a differential form gives rise to a non-trivial cohomology class if and only if it is invariant by the monodromy operator. And to be invariant means exactly this condition for the degrees. Right? This is the explanation. And now in the remaining 5 minutes, I'll give you an example which will play a key role in the future. So if I have an A1 singularity, then you know everything. So the Milnor is just one-dimensional, spanned by the element 1. And so to have an element of this type, we need to have an element of this type. And now what is the condition? So G is the sum of square. And so the condition is that the degree of omega, which is n, this should be equal to 2k. And so we see again that the only interesting case is the case when the ambient dimension is even, and then we get just one basis for this complement. And let's call this differential form alpha 1. Now assume that I have a germ in the local ring as the origin, an analytic germ, and I can ask myself what happens if I have this holomorphic germ is defined in this on this manifold, I can take the cohomology class of this form here, and I can ask what is the relation between this cohomology class and the generator, and the answer is that this is given by this formula. In other words, I have to evaluate H at the origin and multiply with the generator. And now, let's look at a slightly more complicated example. The A2p minus 1 singularity. And this has an equation of the following type. And I leave you as an exercise that we can do exactly the same. And what we get here is the following. Again, for n equal to k. And if I call this differential form alpha p, then I can ask the same question and the answer now is a little bit more complicated. Is coefficient of y1 p minus 1 in H y1 0 0 times, so this is like that, times alpha p. So this is a straightforward generalization, but there is still a big difference between the two results, and this is important to understand. In the first result, I have to evaluate some germ at a point, so the system of coordinates plays no role. In the second situation, it is important to fix the coordinates, which gives a nice equation for the singularity. So a singularity can appear in a bad system of coordinates and still be of this type. So in order to do the computation, I have to choose a good local system of coordinates such that the equation becomes this, and then I can have such relations. And that's why.
So I mean, the point you're making here is that these y-i's are local analytic coordinates.
Exactly, local analytic.
They don't have to be expressible as linear coordinates in the...
No, not at all. So local analytic coordinates. At A, which is in Pn.
So you know, a famous example, a quartic hypersurface, a K3 surface, can have a singularity of type A18 or A17.
Yes.
Very, very complicated. And then it certainly is not linearizable.
Yes. Okay, and so this is a reason why dealing with node, it's somewhat easier, a lot easier than dealing with more complicated singularities. Because for more complicated singularities, we have to do local computations using adapted local coordinates. Okay, thank you very much. So any questions? Because organizers are a little bit... I should ask myself, do you have any more questions?
But I mean, in practice,
Yeah.
for example, if I have a hypersurface with only nodes,
Yes.
then whether or not the V has trivial cohomology
Yes.
is just
Yeah, I have 2 more lessons. I cannot tell you everything in the first 2. So that.
No, but I mean, in general, it's just a difficult question.
Yeah,
I
yeah.
don't see that.
For nodal hypersurface, everything will depend on the position of nodes.
Yes.
And after that, of our ability to construct interesting examples. And so I will explain tomorrow how the position of nodes enter into this picture. I know nothing about how to construct interesting examples. So I know some examples, but I don't have a machine to construct examples. Okay? Thank you very much.